Hello, welcome back. This is Bob. We talked about the thin film yesterday. What is a thin film? Basically, it's the thickness less than 1 micrometer, any material. So today we talk about how to make those thin films. The thin film deposition, basically we use a term called the deposition process, refer to the process making thin film. So here you have a substrate and you're applying a thin film through the deposition process over here. And this material basically is the transfer from the source material into the thin film. Basically is transferring among the 4 different states. It's a solid, liquid, gas, or plasma. The plasma state is basically when the electron after shell of electron are separate from ion but still within the system. So you have the same amount of electron and the positively charged ion. Here that's according to the state of the raw material at the time of forming the thin film. We have a classification of the thin film deposition per the method. And here, that's when the material was in the gas state, you have a CVD, PVD, or IBAD, ion beam assisted deposition. CVD means the chemical vapor deposition, physical vapor deposition. Beside the gas state, you have a solution state, basically the liquid. You can have a chemical solution deposition, electron chemical deposition, or you have a Sojo process. And also can be the self-liquid molten liquid or the semi-molten. Basically, especially refer this one to the metal like laser deposition, thermal spray, that's coating and welding. These two type mainly used for the thick film deposition, and for the gas state, mainly for the thin film deposition. The speed is lower; it's easier to control. And we should see that we need to see a little more here. For the ion beam assist deposition, basically it's mostly of a physical vapor, physical nature. Refer to some people call it a PVD, a type of a PVD, but there's some chemical reaction getting involved. So some people like to list it separately. And here we compare the PVD and the CVD. What's the difference between them? And those both type for the thin film deposition. So they are both the vapor type. They have to perform in the vacuum state. And the reason for using the vacuum, because this one they have requiring high purity. If you don't use a high vacuum, it easily get contaminated by those elements in the air, like oxygen, nitrogen, and there's many other type of contamination. The CVD based on the energy to break down the cursor, and basically the material they use, the source material they call the precursor, and they based on the energy used to break down those cursors, and they have a thermal energy, light energy, or plasma energy. They have different CVD too. Here the process flow that you have a precursor, the material, the gas, and then goes into the chamber. And then you have a crack down those precursors to get the element required for the film deposition, and then you have generate some waste, and you get rid of those, treated separately. One example is the titanium tetrachloride. Or for titanium nitride deposition, you use a precursor, titanium tetrachloride. Besides, you have a nitrogen and hydrogen, the carrier gas and the reaction gas. So this one get cracked down in the titanium and the chlorine ion. Titanium react with nitrogen, chlorine goes to the hydrogen, and then goes out, removed from the system. So you have a titanium nitride deposit on the film. For the PVD, physical vapor deposition, you have no chemical reaction involved. So the source material and the film, they have the same composition, same material. And then you use a vacuum to prevent the contamination. And they have other type. They have ion plating, sputtering, evaporation. And that's why for the ion plating, they have a different type, subtypes. So basically for all those deposition technique, they always have a new technique developed. And they have a new names for the new technique. So for sputtering, for PVD, here there's a general the technique. So first you have a solid material and in the vacuum chamber, and then you have a transfer those solid into the vapor state, and you can be the thermal energy, E-beam energy, or sputtering action. And one example, you have a titanium, like you want to form the titanium film. The source material, you also use the titanium, the same material is the thin film. And you just transfer from the solid into the vapor and then condensed into the thin film deposition. So you have film over here. And then here we give a little more information on the chemical vapor CVD and PVD here. CVD, the vacuum deposition method, and for the solid film deposition. This one you have a substrate exposed to the volatile, the precursor, basically the raw material used to form the film. And then you have a reaction and decompose, then form the thin film on the substrate surface. CVD is used, very widely used, to form the many different type of the thin film, including you have a monocrystal, the epigrowth, those, and polycrystal. Epigrowth we can talk more later. That's a little bit involved, a little more detailed over there. You have polycrystal, monocrystal. Difference between monocrystal and polycrystal, basically the monocrystal, basically the whole thin film is just when all the atoms get lined, perfectly lined. There's a whole crystal, it's just one crystal, and the same orientation and the same aligned. Not much defect involved. For polycrystal, basically the whole thin film on the substrate is many different smaller crystals and aligned. They have called a crystal. They have a boundary to each other. Each crystal is a small group of atoms. They align. It's within the crystal is still good, perfect lined, but between the crystal they have near the transition region. They have not well aligned to each other. Amorphous, basically atom mostly is not, there's no specific rule to follow, looks more like random. That's called structure, that's amorphous material. Here the epitaxy, basically epitaxy, you have substrate and then the crystal grow on the top, and basically when they aligned, you maintain the same structure as the substrate in the film. That's epitaxial. The CVD is also used for purified material and form the new crystal development. So it's a pretty also the broad, the spectrum or different technique can be divided. And one good, excellent, the advantage for the CVD is can modify the film property, and especially like the electrical or the optical property of those films by the adding the new element. And that process is called the doping process. Basically you're adding the impurity, like any material. If you have a thin film, if you adding some controlled impurity, you can change the electrical property, basically change the resistivity or make the film whole resistant of that film. So you can use the CVD, you can adjust in the film the property, control the property of the film. Type of CVD in general depend on the energy you used for the cracking the precursor. It can be the thermal CVD, light CVD, or plasma CVD. Here the picture we show the sample, basically the typical CVD system. It had the power and the control unit here. It the precursor, the handling unit, basically the one you have a gas, precursor the gas, and you want to have a treatment, control the flow rate, the temperature, and also you want to mix. Sometimes they mixing the different precursors, aiding the impurity element. For this one, the precursor, the handling system, the unit here. And then they introduce this side for the reaction unit. Like here, reaction unit usually like a quartz, it's a tube. And the reaction happened over here. The gas get involved inside, and they have a reaction in the chamber, deposit film on the substrate, and then the waste got pumped out from the system and get treated separately. So this one, the reaction, the chamber, the reactor, when it's in the working state, you see the get a heating, have energy, thermal energy, and get heat up, hit the control at a certain temperature for the reaction. The next one, we talk about the physical vapor deposition. And this one, again, is a vacuum deposition method. You want to maintain, control the environment to control make sure there's minimize the contamination in the air for the thin film and the coating. This one is transferred from the source material and into the vapor, then condensed to the thin film state on the substrate. It's used, this one they used also the very wide used, and for requiring especially mostly the like a single element like metal and some compound also. So require the thin film for the mechanical, optical, chemical, electronic function. And then earlier we said like titanium, from titanium into titanium. That's when it's widely used. Also the other nickel, aluminum, copper. So there's many methods that can be deposited this way. The type of a PVD you can have during the evaporation or sputtering, ion plating, and also the MBE, molecular beam epitaxy, also adding more, increasing the type of method. We always have the new technique developed. So here I want you the evaporation sputtering is so used very widely, and so here the picture showed how it works. This one is the E-beam evaporation, electron beam evaporator. This one you have a source material put in the crucible here, and it's water cooled the crucible. You have a source material put inside, and you have electron. They have an electron filament. This one have increased heat up, and you have a voltage pull electron out, and under the magnetic field, it's going heating on the source material, heat up the source, and transfer into the vacuum vapor state, condensed on the substrate mounted on the top. Over there, it's cooled and condensed, forming a thin film on the substrate. That thin film, you have a controlled thickness, precisely controlled how thick you want. Note this one, normally in the current electron beam, this one, the source is maintained in the vertical and then goes to the side. This one has the advantage, you may have some particle of dirty stuff fills down, and this one, it doesn't easy to fill down the filament, so you can have a longer lifetime. So this one a good advantage of that. That's evaporation. Beside the E-beam, you can also have the thermal evaporation. Basically, use the heat, just use the heat up the source directly, either with electro energy, the heat up, resistive energy heat up. That also works. The sputtering system. Here's the DC sputtering system. This one is in the vacuum chamber. You have they call the bias. You basically you charge on the substrate, and this is the source material. This one on the substrate is positive charge, they call it anode, and this source material that you call the negative charged. The reason for negative charged over here, you use like a gas element like argon. You basically break down the argon, you form the argon ion. That's positive charged, and they get electrical negative charge, get attracted here. High speed movement over here is the bombard and heat up the element, the source material element. This one come out and deposit on the substrate. This action is just like shooting, like you're shooting the gun. Basically this one, the source material become the target. And that's the reason people call this one also as the target, spotting the target material and atom spotting deposit on the substrate. So this one is a very good, excellent technique we use very widely, like computer chips, thin film, basically for the metal. So wide deposition is almost become a separate industry, the separate the supply for the equipment for that. So over here, today we talk about how to make the thin film, and we talk about the technique. The process for making thin film is called deposition, and they have depend on the nature, the energy used for the deposition and the material status. We have a different type of technique like CVD or PVD technique, and then for the CVD they have each one have a subsystem of a deposition technique. And here that's when we show the evaporator and the spotting system. So that's today's topic for how do we make the thin film. And if you are interested, please subscribe to this channel. We'll bring more topic in the future. Thank you.